I'm going to make a short video series about upgrading the 858D or modifying it with a custom microcontroller. So over at the eevblog electronics community forum, there is a large thread, like 18 pages, and I've done a lot of research, as you can see. So I've ordered components. So you can see here there's pictures of people modifying the board, and there are several versions of it. So this is the one I have with the MK18D something microcontroller. Others have the green board with the 80 mega or a Samsung microcontroller, so you need different modification boards. There's lots of videos on the YouTube, and this is not the board I've ordered. So the real cool thing is that you can use an 80 mega, and therefore you can use Arduino. So Arduino software to compile and then upload. So yeah, and I'd like to explain this fantastic reverse engineered schematic. So therefore and that will take time, so I'll cut the video in two. This part will be just the schematic, and the next one I will tear this one down and then replace the socket and see how this one differs from the this is water, by the way. This schematic. So yeah, cool stuff. I hope this will be interesting. So I also have to program from the Arduino, which I haven't done before. 866 programmer. So and this is supposed to work. It has in circuit programming also. So yeah. This is from the eevblog thread. It's from 2013 November up to 2016, and maybe I'll post a link there to ask for some firmware and stuff, but maybe I'll do some myself also. Anyway, the driving force behind this was asked by someone, and the device never showed true air temperature at heat up. But it did show accurate when the cooling down. Cannot go below 100 degrees, that's also a point. And the other thing, someone saw also they had a gigantic overshoot. Now I have measured mine and I can't see any overshoot, but the device never showed true air temperature at heat up. Well, mine actually does, but it goes away. So what the firmware they are making, they're taking out the microcontroller, which is locked, by the way. You can't dump the internals. There are three different ones. There's at Mega 8, there's a Samsung one, and there's a MK1841D3, which is well, I have no idea what that is. Yeah, so the firmware that this guy Madworm. So this firmware that this guy Madworm wanted to make was that it showed the actual temperature all the time, or within 3 degrees of the setting. So because there's you never get it to stay there all the time, you know, it has to regulate. And also you wanted to remove the overshoot, so or undershoot. So if you change the air flow, the device has to start to regulate again or compensate. So, and it has to be fast enough, and you have a PID regulator, so which has to be tuned. So yeah, so and there's another guy called the Veguibas. Now Veguibas was a guy who started looking at the MK1841D3. He also looked at making it such that you can monitor the current coming back from the fan motor, so you can see if it's stalled and such. To get that, they put a current sense resistor in series. I think you have to cut a trace for that. And then 2014 at July 24th there was a nerd fight. Well, that's very typical, isn't it? So it's like for every forum there's a nerd fight. Yeah, and then this reverse engineering came along in 2016 January. It was talking about redesigning the whole board, but it hasn't done that. Probably life got in the way, you know. So then the VGUI was demonstrating a fervent or a rework station called Calip 858D+. So yeah, so that's one. It's the one I'm looking for. So, and then you have the Giant Gnome is supposed to post his SMD version of the board, so which I have ordered. And there are also suggestions to add a heatsink on the tip 122, the one for voltage regulating the fan speed. So, and also check the earth of the nozzle. And then there's another firmware update. So yeah. This is a website called Heart of Technology by Christy 4M. He has done an excellent job on reverse engineering this Atom 858D. It's not actually an Atom because Atom is just the name, it's the 858D. Now this has an Atmega 8 and mine has an another type of microcontroller we can look at. He has a full diagram, but this is his sections, and these sections are really logical, so it's fantastic. Anyway, so this is the mains part. As you can see, mains comes in here, it's live, neutral, and then it returns heater drive. So you can see here I have a X2 filter cap, you know, those square ones, rectangular ones, and then discharge, so you don't get a thing from when you touch it when you have it unplugged. You have the low voltage part, which is just a isolation up to isolator. So the microcontroller can switch on this diode, and then this strike is conducting. So, and when that is conducting, it's conducting power. When the live is on the positive side, it provides power into, or current into this triac, and it turns on. And when it doesn't provide any power, this resistor will keep it off. So, and you, to turn it off, you actually have to zero the voltage both over it and then on the gate. So because it's a point of no return, so to speak. And then you have some filtering here. I'm not sure why these are here. Yeah, so that's about it. You can see that the live comes up here. It goes through this, when this is on anyway, it goes through here and then out on the heater. So that's why you don't have a big transformer. So let's move on to the low voltage supply. I really love these diagrams, it's excellent. Here you can see we have a only halfway rectifier. So here comes 10 volts from the transformer and 25 volts also. So you can see you get from 10 volts AC, you get 14 volt DC, and we have some filtering. Save it 805 regulator, which gives you 5 volt to the microcontroller, and some reference stuff. So, and we'll look at that also. So what is this then? So when the voltage shares goes positive, then you charge up this one, but when it goes negative, this one turns on and charges this one. So you get negative voltage share, this pulls the voltage down here. But why do you have a resistor here? That's kind of interesting, isn't it? So, and you get minus 14 volt here. So let's see why you need that. So here we have the temperature sensor amplifier. Here you have the 5 volt that was generated in the other schematic, negative minus 14 here. So, and remember you had a resistor, and I think the reason for that is for filtering actually. So it's still minus 14 volts. This one is reversed because this is the positive side and you have negative voltage, so this isn't doing anything. Might have something to do with discharging or something, not sure. And it drives the negative side of the amplifier, and the reason for that is because, look, here you have 0 volts, right? And from a thermocouple which comes here, temp sense, that's a thermocouple, which isn't amplified, it's like microvolts. It's really low voltage, so you need a low noise amplifier. You need it to work down around 0 volts, and op-amps don't perform really well at 0 volts, so therefore you put the negative input here below 0 volts, such that they can operate properly. So, and you can see the way the op-amp works is that it tries, you can see the temp sense comes in on the non-inverting input, and then that output is fed back into the negative input, and what the op-amp tries to do is to keep these two inputs the same, so the input impedance is very high, because there will be no current through here, and there will be no current in here, or very little anyway, because this point here is the same as this one, and then you can't get any current through here. So let's say this voltage is rising, the output is rising so much that this one gets to the same point. Now there is some voltage division here, so that means this one has to go much higher than this one. So therefore you get gain. So and that gain you can control here, and we will also see that when I do that, it's not very accurate. So you can calibrate it to like 280 degrees, but then when you measure at 150, then you get like 20 degrees off or something. So yeah, so that's not really great. You do have a microcontroller, so there's no reason why you would want to do that here, really. But that's the way they have made it. So this is just filtering of the author didn't understand why this was here, so it causes a sort of a voltage division of 35 microvolts or something. But someone else said, and I can tell you that too. I know that for a fact. So some of these models you can disconnect the heater, and therefore you disconnect the sensor, and then this one will fly up to 5 volt, and the output will also fly to 5 volt, and the microcontroller will see that it is disconnected or something is wrong with the sensor. So this is the microcontroller part. You have 5 volt on the top, and then you have a reference. Usually these microcontrollers at Mega 8, they have their own reference. This is the same device I use in the C64 Saver. So when you connect it like this, you get 2.5 volt reference voltage here. So that's that part. You have the trike drive, which goes up to the isolator. You have the LEDs here, which is driven in a multiplexed display fashion. You have something here which is not connected. You have fan on, which goes to the one we already looked at. This can choke the voltage supply. The read switch, which is an input. So read if the wand is on the stand or not. There is a read switch in this blower, which activates when you get a magnet close to it. So put the screw here, you can see it sticks. Yeah, and 2 buttons, and then that's about it, I think. So it's not very interesting. You have voltage sense also for the fan. So yeah, I'm not sure why it wants that, but then you have the full schematic. So really great. I really like this one. So you can see on the right side you have the like there. It's really great. Then you have the transformer and everything. You have a reed switch. So everything outside is square, or a rectangle. It's external parts. So yeah. So since this is a multi-series video, so a small series, let's look at the fan driver circuit again, which looks a bit kind of interesting, I think. So now you can see we have these potentiometer here, and you can also notice it doesn't go down to 0. You can't turn it off. You don't want to burn up the the plastic here. If you turn off the fan, this one will overheat, or it can overheat anyway. So, and it goes up to 8, so it has 2 limits, upper and lower limit. You have the power coming in from the rectifier, goes through a transistor and then out on the fan. Now the control part is here. This is the pot. These 2 resistors controls the upper and lower limit. That means if you wind this pot all the way down, you still have some resistance. So you can't turn it properly off. So now, how does this work? But whenever you see a large transistors like this in series, where the emitter is connected to the output voltage, you can look at it as an emitter follower. However, there's a twist plot here. The thing is, when this voltage rises, so this device pulls up to the 36 volt. So when this voltage rises, so will this also, until the voltage is so high that this one turns on. And that is controlled by the zener and this emitter here. So then it starts to shut this one off. But if this one is shut off, then there's no voltage out there. So, but if there's no voltage, then this one shuts off again. So they regulate each other. So therefore you get a set point. Now, if you turn this one down, then this voltage has to go higher before this one turns on and regulates this one. So it works the opposite way. So if you turn this one up, if you turn the pot up, the voltage here doesn't have to rise so much anymore. It will reach the set point here, and this one will turn on earlier and then turn this one off. So, but it's not really turned off, it's turned into the linear region. So the transistors have 3 regions by definition. So one region is when it's off, so that's okay. And the third region is when it's completely on or saturated. That means there's enough drive here to keep it on, even though the voltage over it changes, it's still just completely on. And then the second region is when you have linear region. So this one acts like a resistor instead. So it's not fully on, it's not off. You can look at it like you're changing the resistance here by changing this pot. And you also change the voltage here by changing the voltage here. So why do you do that? Well, you could have used a resistor which was high power and just connected in series and drop all of this. But that's expensive and it's very large and it causes a lot of heat loss. Well, this one will be quite hot actually, so that's not the point. It's more a point that it's expensive. So in this way you get a small current down here. You can see 5k, 10k, 7.5k, so that's over 22 something, 22.6k. And then you have a small current here and small current going into the base, limited by these resistance here. And this arrangements will put this one in the linear region. So the other thing here, you can see from the microcontroller, you have fan on off, so you can choke this base of this bipolar transistor. And when the voltage here is low, this one, you can look away from this one. So yeah, so you can also look at this circuit in this way. If you think that the voltage here is lower than what this turns on, you can look away from it. Sort of does whatever it needs to this net to charge up this capacitor and everything. And when it comes to a certain point, this part comes into the circuit and starts to regulate. So make some negative feedback. So I don't know, it's a very good explanation. So let's continue. This voltage is also divided such as it gets into the range of the microcontroller, so you can read it back. So yes, that's about it.